Well, ECHO has been talking about the benefits of moringa for years. And some of you know that in addition to the nutritional benefit of eating moringa leaves, moringa seeds are effective in purifying and treating water. And this morning, Dr. Stephanie Velegol, an engineering professor at Penn State, is going to take that discussion of moringa-treated water to a whole new level as she describes the creation of sticky killer, MOCP, sand. So Dr. Velegol, I'm looking forward to this. Can't wait to hear what you're going to say. Let's welcome her this morning.
Thank you so much. It's just been so wonderful to be here, and I've been inspired by all the work that you are all doing, going on site yesterday and seeing the farm, and I love the appropriate technology tour. It really inspired me to bring that back to Penn State. One of the things in my life that are really important is to show students, and I have a lot of students at Penn State, it's a big campus, is to show those engineering students that they can use their technical skills to make the world a better place. And our students are really craving that, and so being here has given me even more ideas of how to show that. And so what I want to tell you about today is some work that I've been doing probably since 2010 when I first heard about moringa. And so wait, before I do this, I'm going to hit this to move it forward. Okay, I'm going to try that. And yes, we're making sticky killer sand. And so it's going to be a little bit on the technical side, but what I really hope to show you is that when we really dig into the science, there's a lot that's been discussed about moringa, and I've heard through the years it can cure everything. I don't know about any of that, but as a scientist and as an engineer, I decided if we're going to really use it, we have to show the scientists what's really there. So I will tell you a story before I tell you a few other stories about when I first learned about moringa, and I'll tell you how I learned about it in just a minute, but there was a woman who came, Vandana Shiva. She's an activist from India, and she's an activist on women and water. And she came to speak. She was hosted by the law school and global programs at Penn State, and she spoke about women only being willing to walk about, I think she said, maybe 10 kilometers for water, and then they give up. And it was really inspirational to think about the water part of that. And so anyway, I went up to her after, and I knew that moringa grew in India. And so I said, just like a good American, ignorant person, I said, do you know about moringa trees? Because I was so excited to learn about it. And she said, yes, I know about moringa trees. And I said, do people use them to clean water in India? And she said, well, in the villages they do. And I said, well, what about in the cities? And she said, well, the Western world hasn't accepted it yet. And that was sort of a challenge to me to say, if we're going to really see what this thing can do, we need to explore the science. And so that's what I hope to talk to you about today. I hope to tell you and show you that I have a claim that the seeds from 6 trees can clean water for 1,000 people. And I always get the question of how long will it last. I hope to show you that it will last for years. I will need some help in doing this on the ground at some point. So I am, as a scientist and not someone who works in those areas, open to talking about that. So before I talk about that, I just want to thank Ricky Bates, who many of you probably know here at ECHO. It was a conversation, so just how I got into moringa. I had been asked to teach water and wastewater treatment at Penn State. I had never taken that class before. I didn't know much about it. So the best way to learn is to teach it. And so I taught 1 semester of that, and I taught many, many after that as well. And I really became passionate about this issue of clean water. And I went to the pastor of our church. We were having lunch, and he was going to Myanmar. And we were there to talk about something else. But I said, well, tell me about water in Myanmar. Tell me, just tell me everything I can learn about it. And he said, well, you need to talk to Ricky Bates. He has these, I don't know what he called them, magic seeds or something, that clean water. I'd never heard of them before. So I caught up with Ricky and said, tell me what you know. And he said, well, I don't know, this is what, there's something about the seed that has something interesting in it. So I started reading everything I could, and that's sort of what pushed me towards this research that I've been doing for a while. So just before I get into, again, the details, I just want to thank so many students that have helped. I've had dozens of undergrads on this project over the past 8 years or so. But these are the students who've worked on the project, the part of the project I'm going to talk mostly about today. So you can see we have students, graduate students, undergrad students from civil engineering, chemical engineering, and I will say they just love working on this, and I love being able to share that with them. Okay, I think that's all I wanted to say. So thinking about the big picture of Moringa, and I'd love to have more conversations about this with you all before I get into the details, but we really have been starting to think about Moringa as part of a food, energy, water nexus. This is a big buzzword now in the scientific community. NSF has these huge grants that they give out for this. And so we're really thinking about this in terms of, all of you probably know about the incredible value of the leaves. We're looking more at the seeds, and so if we take these seeds, we can squeeze them. Many of you have seen, I've seen the, can't think of what the presses on site, and so you can press the seeds and get a valuable oil. And actually the Body Shop, many of you know, has a Moringa line, and they're getting all of their oil actually now from Rwanda. Start doing some collaboration with them there. But the good thing is when you squeeze the oil, you get the seed cake. And the water treatment stuff that I'm going to talk about is in that seed cake. So we're not competing with oil. And then my proposal, well, I'm going to talk mostly about this part right here, but I just want to open up, since this is such a great community, to think about, there's been some evidence, and my hypothesis, well, let me back up for a minute. If you feed these seeds to animals, just the raw seeds, there's some anti-nutritional components in there. Many of you may know that. There's been some work already showing that if you remove the oil, and then you remove the stuff that, the protein that I'm going to talk about today, then that seed, that whatever's left of that seed cake, which is a lot, maybe half of it we could get back, that actually will be better for animals and will not have the anti-nutritional component to it. I'm not a chicken farmer, so I'm not going to be able to do those studies. So if anybody's interested in talking more about that, I'd love to talk about that. So there is already some literature showing that some of those anti-nutritional components will be removed in those processes. And so that could be really something to kind of pull this all together. Okay. But I am going to talk primarily about the water piece. That's my expertise. Okay, and so many of you live this and you know this, that clean water is such a global challenge, and it affects primarily children. So these are the statistics that drove me into this research and keeps me in it, in trying to find a sustainable solution. You also all know that this really only affects low-income countries. This is not something that we deal with as much in this country. It's the number 2, actually it's changed from I had a statistic from 2012, I think, and it was number 3, now it's number 2, cause of death, according to, I think this is the World Health Organization. Okay, so when I started teaching water and wastewater treatment, I said, well, I'm confused. Why can't we just do what we do here and save all these lives? And when I looked into that, of course, one of the big answers is infrastructure. We have an incredible infrastructure, and the US government invested in that in about the 60s. That's difficult to get that kind of money, and then we all still pay for water and wastewater in this country. There are a lot of other things that I've looked into. One of them is something like a life straw, which is very effective. It's also expensive, and it needs to be imported. Speaking of Haiti, we can boil our water, but as you can see, and as many of you know, that's using a natural resource that we may not have and may not want to use to burn things to boil the water. Although I liked on the farm yesterday having that solar heater. That was really neat to see. And then, of course, bleach. Bleach works very well. This is really just chlorine. We call it chlorine. I talk a lot about chlorine in my classes. Very, very effective. And so anything we do has to compete with chlorine. However, chlorine has a taste. We've all gotten a little bit used to it in the US, but it definitely has a taste to it. There are also issues if your water is really turbid and you add chlorine, you're going to form carcinogens in the water, and that may be a bigger long-term issue, but there are some issues with chlorine. And so the biggest issue here is expense, availability, and acceptance. So looking for a solution that would be more acceptable in parts of the world. And that's where these moringa seeds come into play. So I'm speaking to the choir, preaching to the choir here, but most of my crowds don't know about moringa, but as you know, moringa grows in these equatorial regions where it's dry and hot, and overlaps a lot with malnutrition and lack of clean water. This is actually the first moringa tree I ever saw in Rwanda about 1.5 years ago. So I've been working on this a long time I saw one in a greenhouse, but live kind of, and real. So it's very exciting to see that. But one mature tree, at least I've read, can produce 15,000 seeds a year. So that's a lot of seeds. Okay, so here's where kind of the science kicks in a little bit. So when I first learned about this, this kind of got messed up, but that's okay. When I first learned about this, I learned that the seed, in the seed, and this is in some papers of mine if you want to get the actual amino acid structure. Whoops, back up. Oh, I'm going backwards, hold on. Can I go back? There we go. We know that the part of the seed that's responsible for water treatment is a protein. It's a small protein. Some scientists call it a peptide. It's about 60 amino acids. And the amino acid structure is known, the sequence. And what's really interesting when I first looked into this was that researchers had already determined the part of the protein that was responsible for killing bacteria and the part that was responsible for flocculating bacteria. So the way that this works is that the protein is positively charged. Most things in nature, including all the pathogens that make children sick, are negatively charged. And so the reason we call it a flocculant is because you have two pathogens, or many, and they're negatively charged. So they don't want to stick together. They don't want to clump. And they're also not going to settle in water because they're too small. They're about a micron. Well, they can vary up to 10, but at least the micron ones in viruses, of course, will not settle. So you see them. If I had dirty water here, you would see, you shake it up, it stays. You guys have all seen dirty water. You know what I'm talking about. And so sometimes if you let dirty water go, it'll settle. The big stuff will settle to the bottom, but there's still those microorganisms you can't see, and they're dissolved, and they won't settle in the time frame that we want them to. But if we add a flocculant, alum is a typical one that we use in the US, but moringa does the same thing. It will cause those negative particles. It will neutralize that charge because it's the opposite charge, and it'll cause them to flocculate together. Once they flocculate together, they're big enough that they settle with gravity. That's how flocculation works. And we do that with alum in this country. And moringa works very well as a flocculant, and we'll talk about that in a second. But that's sort of what we knew about it. And so they were even able to identify, it's hard to see here, I guess, but that this is the part of the seed that causes flocculation, and this is the part that causes it to actually kill. So in the research that we've done, we've actually shown the mechanism, the antimicrobial mechanism that moringa has to kill bacteria. And so this was kind of a nice paper, actually. It was mostly my colleague who's in this area of antimicrobial mechanism. But what he and I were able to show was that this is actually E. coli vesicle. And so E. coli, and I'll show you this one too, I guess it's a little better, easier to see. This is actually an E. coli bacterium, and the inner and outer membrane fuse. So the inner and outer membrane are also negatively charged. So the presence of something positively charged causes those two membranes to fuse. Once they fuse, that bacteria can't reproduce, which means even if we take it in, it's dead. So I don't know if you know this is kind of a joke I say to my students all the time, but, well, it's maybe insensitive. But bacteria, you know, when we're dead, we know we're dead. Our heart stops beating, right? But when bacteria die, it actually means they can't reproduce. So there are a lot of people in the world, you know, walking around who, if you were a bacterium, we would say maybe you can't reproduce anymore. But just so you kind of get that vision. I know it's funnier when you're younger. When you're older, you're like, hey, you know. But anyway, but that's kind of a way to think about what do we mean by killing pathogens. We really mean they can't reproduce. They may still be alive. They may still be a balloon of, you know, but we really, if they can reproduce in our bodies, that's what's going to make us sick. If we swallow it and it's dead, it's still there. Okay, sorry. This is, if anyone wants to look it up, that's the paper that we did there. Okay, so you all know this. I learned it from reading probably work that's been done here. So the way that Moringa typically has worked, and the way that you all show it at the thing, is you take these seeds. We did this in the lab. This is just dirty water from our bike path or something. We crush the seed, we add it to water here, and we can see this flocculating and settling to the bottom. Okay, however, there are two problems with this technique that I learned when I was doing all my research at the beginning. One is that this water contains organic matter. It contains other proteins. It contains carbohydrates. It contains food for microorganisms. It would be as if you were to have chocolate milk or orange juice or any kind of drink that has sugar or carbohydrates in it, and you were to let that sit out overnight. Most of you would not drink it the next day. You might drink water the next day, but you probably wouldn't drink something that had sugars and carbohydrates in it. It's the same thing here. So you can drink this water right away, but over time, those bacteria, is my mic weird? Okay, just me, okay. Over time, that bacteria will start to grow. And we've actually heard reports from people in Haiti who say, this is terrible, the water stinks, I'm not gonna use this anymore. So that's one caution. Certainly in a bind, you can use it, drink it right away, but if that water, even if you decant it, oops, oh my goodness, I'm getting used to this. Even if you decant this water, it still contains this organic material. It still contains that dissolved food, and the microorganisms can grow on that. So just a little cautionary tale there. The other issue is that, as you can see, again, this is better than this, but it's not really up to US standards. It still contains those microorganisms, and there's still some concern about that. And so we've done these experiments in the lab, and I've seen lots of papers on this. You really can only get 90 to 99% removal. And the 99% removal is only with really turbid water. And typically water, unless you're really in a rainy season, isn't that turbid. And so, we needed to get better removal than that. Okay, so the first thing I want to tell you about is sticky killer sand. So this was the idea I had to get rid of to have a process where you wouldn't have this regrowth. And the idea is simply that, so it's not showing up too well there, but this is a sand particle. Sand is also negatively charged. So if you crush seeds and add them to water, the cationic protein will dissolve in water. You then add sand, and that cationic protein will stick to sand irreversibly. And then you can rinse the sand. You rinse away all the organic matter, so nothing is going to grow. And you're left with a now cationic or positively charged sand particle, which now becomes like a magnet for microorganisms. The microorganisms will then stick because they're negative, and this is positive, so then they will stick. That's the sticky part. And that all happens without any fancy equipment at all. And over the years, people have said to me, and people have done this, and there's lots of work doing this now, you isolate the protein, and then you stick it on. Yeah, but who's going to do that in the lab? We've done that in the lab, but you all are not going to take that back to your communities and say, we're going to have this great, huge system for isolating a protein. My point is you don't have to. The protein isolates itself because it preferentially adsorbs to that sand surface. So this is no fancy equipment at all. So basically, you crush the seeds, you add them to water. We do filter it. This is not really necessary, but we do filter to get rid of all the big chunky stuff that doesn't quite get removed, but you do not need any special filter paper. You can use a cheesecloth. You can use a piece of cloth. You can use anything that will catch big chunky stuff. This does not require extensive filtration. We do put it through a smaller filter because so many of the way that we assess what's in the water is techniques that need clear water, but you don't need that actually. And then you add that seed mixture. This should say add seed mixture to sand, not water, sand and water, and mix, and then you rinse to remove the organic matter. So it really is that simple. So when we first did this was just so exciting. We knew it would be sticky. We assumed it would be sticky, but then we found out that it's killer too. So briefly, this is a bare sand surface, and this is we call it F-sand, okay, functionalized sand, I don't know. So this is a functionalized sand surface. So this is coated with that Moringa protein. These red or green things are actually E. coli that we grew in the lab, and there's a stain called backlight that if they're red, they're dead. If they're green, they're alive. So we can get into more details of that if you want, but let's just say for now, what we found is that we captured the E. coli on the surface and they died. So we confirmed sticky killer sand. It was very exciting. However, we did this in like a batch process. So we did it like here, we had the sand and water and sand. This was actually kaolin, just something we used to mimic turbidity. And so you can see we got to remove the kaolin, but really we're still only at 90% removal. So that process of a batch, putting it in, mixing it up, I saw yesterday they have one of those rollers, I thought, well, we could do it that way, put the sand in there, but we're not getting as much removal as we would like. And one of the reasons for that is that we didn't have enough contact. So we know the things will stick if they hit it, but the question is, how do we get it to hit it, right? So then we decided, well, we have all these sand filters, right? Slow sand filters, rapid sand filters. Every swimming pool in the United States has a sand filter associated with it. Every surface water treatment plant in the United States has a sand filter. I don't know if you all knew that. The reason for that is that chlorine won't kill Giardia and crypto. It definitely won't kill crypto, and it is difficult to kill Giardia. I don't know if you knew that, but that's kind of scary in the US. Anyway, so we thought, well, what if we put our sticky killer sand in a column, right? So a regular sand filter will not remove E. coli. A slow sand filter will, because of that schmutztica that, I love saying that, because anyway, it will work. But as many of you probably know, slow sand filters take a while to get generated. Okay, so that was our idea. But we needed a lot of questions. So I've been talking about this for a while, and the first set of questions is more practical. And so we had questions like, well, wait a minute, how many seeds do we actually need, right? And then how long is this process going to take? Like, how long does somebody have to sit there and stir this? That may not be sustainable. And then how do we know if it's working? How do we know if we actually have a seed? Not all seeds work the same. This is a natural product, right? We can't take every single seed we use, send it to the lab, and get it back in time to make this stuff. And then we had a question of, okay, so I can make a filter this big in the lab, and I can tell you and I'm going to tell you what happened. But you don't want a filter this big, right? You want a big filter or a small filter. You either want an individual filter, you want a community-sized filter. So as engineers, chemical engineers, this is what we do. We take processes and we scale them up so we can make it bigger. And so we need a model to do that. So I'm going to talk a little bit about that. And then finally, the big question is always, well, how long does it last? This filter is now more like an activated carbon filter than a sand filter because the stuff is stuck to it. And we can't get the stuck stuff off. We could with some other techniques, but how long until it's done? We need to know that answer. And we need a model for that, right? We need a model. Okay, so the first question is, how many seeds do we need? So what we did was we used a model surface, and we looked at the charge. Okay, so we looked at how many seeds per surface area of sand, so we could vary the diameter of the sand. And without getting into too much detail, we found that the surface charge goes from negative to positive at some amount of seed. This is a log scale. Anyway, so then we said, okay, now we're going to put these things into a column and actually test it. So what we're using here is we're using a 1 micron particle. It's fluorescent. It just helps. It's a lot easier than growing E. coli, and we can measure that in the lab. 1 micron is the same size as a bacterium. That's why we chose that. And it's also the worst size for a sand filter. Sand filters do not remove 1 micron particles. So here's our sand filter, obviously very small. And anyway, and then our sand size is also small. We had to scale it all down. It's about 100 micron. Typically, a sand filter is more like 500 micron. Okay, that's fine. So then again, we used these same concentrations, and here's what we found. Okay, so log removal is 3 log means 99.9%, and 4 log is 99.99%. And so we really want to get more like 4 log, 3 log removal. And so what we found was that with this, let's see, this should be blue, but that's okay. These two, actually this one just was slightly lower. So we picked the red one. So at this seed dosage, we can get 3 to 4 log removal of our particles. So that, and we can scale that up to say whatever size sand you want, but that tells us how many seeds we need. That's the bottom line there. Okay, so we chose that one, and then we said, okay, when we first started this, we had a 1 hour mixing time, so seed into water, mix for an hour, right? Some of you are looking at me like that's never gonna work. And then filter that, and then seeds and water, put it in with sand, mix it for an hour. You're all imagining this is a no-go, right? Immediately, okay, and you're right. And so we were doing that for years just because we just wanted to get data, but then we said, okay, we gotta slow this down, gotta do this faster. And it turns out that, we actually can get it down to 5 minutes. We do not, so 5 minutes of mixing the seed with the water, filter it, 5 minutes of mixing that solution with sand, rinse it, that's it. So we were able to cut the mixing time down, which was great, because we had some people try this in the field, and the pictures of them like, really, we have to keep mixing, this is really bad. So we were very happy to say to them, it doesn't take long. These things happen quickly. We did the same thing here with, don't worry about what the y-axis is, but we wanted to see how sticky it was, and we looked at different kinds of seeds. So we had Haiti seeds, Nicaraguan seeds, Chiang Mai from Thailand seeds, and we also had seeds from India, and then down here is our regular sand. So you can see that whether we have 2 hours of mixing or 10 minutes of total mixing, we're getting very similar results. So that's good. That also means we're seeing consistency among the seeds, different seeds that we have been able to obtain. Okay, this is exciting for me because I saw something similar to this at the field or on site yesterday. You guys had another kind of stick test with the salt and the corn, yeah? And so I was like, oh, I took a picture of it and sent it to my students one of my students who kind of discovered this. So we have a stick test. We actually did this in Rwanda and it worked. So basically, when you turn the sand into sticky sand, that means it's also going to stick to plastic and glass, because plastic and glass is negatively charged. So if you make the sticky killer sand, and then you put it in, I know this is very scientific looking, it does not have to be a scientific looking thing. We did it in Rwanda, and they had like a plastic container. You can do it in a plastic water bottle. I should have shown that picture instead. And if this is regular sand, there's water in here too, you can't really tell that, but there's water in here too. And you can see the regular sand, there's like kind of a clump there, but you can see the sticky killer sand, or the F sand, is sticking to the surface. So as you rotate these things, you see it sticking. That's a quick way, and we've confirmed that with other scientific studies, it's a quick way to say, yes, you've reversed the charge, it should at least be sticky. That's very, very important for practitioners, right? Because if you say this is clean and now this is going to work, and the seed for some reason doesn't contain that protein, that's bad news. So we were very excited to have something on the ground. Again, we did this in Rwanda, just grabbed some dirt off the ground, threw it in, and it was sticky with the seed. So that was very exciting. So sticky test. Okay, this is where it gets a little more into chemical engineering, so I won't stay too long with this. But just to show you, okay, some of you are going to go to sleep now, I know. I just showed this big equation. But so this just is a model. This is the bottom line. So it's a model to say, can we predict? I mean, you guys are all maybe thinking in your mind, okay, how big do we need to make this thing, right? So how big? So the question is, okay, so L, that's how tall it is, right? The diameter of this thing is the diameter of the thing. I was thinking we could do it with bamboo. Saw that bamboo yesterday, right? You're thinking maybe a PVC pipe, whatever you have, right? So if you tell me kind of what this is what I have, and then we also need to know the size of the sand particles, right? And so that is all going to go into the model. You're going to say, well, how much can you make? Well, that's going to go into, oh, watch this, sorry, it's very scary. But, but there are other things in this model that get kind of crazy. But for example, hopefully you're thinking, well, what about the flow rate? How much flows through there, right? That's all in this stuff. It's so fun. Oh, here we go. We're going to talk more about this. Okay, we're going to skip all this here for a little bit. Crazy. But basically, here's the model. Okay, so the model says the particle, say the pathogen, is coming through the sand filter, right? And this eta, this N-looking thing, it's like Greek or whatever, that says of the number of particles coming through the filter, how many of them actually hit a surface, right? They can't stick if they don't hit. And how do they hit? Well, they hit because of either gravity, or they come through because of the way the fluid is moving, or sometimes if they're small enough, they can diffuse randomly and hit the surface. That's all that's saying. There's a bunch of equations, crazy people. But that's all that's saying. And so we need to know that, and that's something we can design as engineers. And then the alpha, that A-looking thing, the red one, that just says of the number of particles that hit the surface, how many of them stick. We call it sticking coefficient, right? And that's the thing that we're going to actually measure. So what's interesting, and this is really important, not that you need to know the last equation I showed you, but although I'm certainly happy to discuss it at more length, but is that this is important for sand filters in general, is that so this just says like whatever, how many of them hit, and it's minimum. Basically, the effectiveness is the smallest at 1 micron particle. So that's where an E. coli is. That's where bacteria are. That's where the problem is. That's where people are getting sick. Again, sand filters work very, very well for Giardia, cryptosporidium, things like that we are concerned about because they're big. Giardia and crypto are up here, so gravity helps them. But for an E. coli, it doesn't. Okay, so we were able to use that model, and we were able to basically say that according to this model, 80% of the particles that hit a surface stick to our F sand, our functionalized sand, our Moringa sand, where only about 1% stick to bare sand. That made sense to us. So we said, okay, this model is working if we get a number that is consistent. And then we looked at different ionic strengths, so different salt. So depending on where you are, you may have a salt that is water that has anywhere between, usually not 0, maybe 1 to 10 millimolar salt. You're not dealing with ocean water here. And so among all of those salt concentrations, we see the same effectiveness. So that was interesting. That's good. We also changed the flow rate, and we see some agreement. We're still not sure why we don't get perfect agreement. This is the model, and this is the data. So we're seeing some reduction in flow rate. We still have to look into that. When we change the sand size, we see consistency, we see agreement. All this is just to say that we have a model that works. If we scale it up, we scale it down, we change things in the model, it still predicts the removal. That's good for us. Okay, the next question then we had was, okay, so hopefully I answered the question, can we model this? The answer is yes. At this point, at least for a 1 micron bacteria-like thing, we can model this. Okay, the next question is, can we model how long this filter will last in the field? And so the way that I'm addressing this issue for now, and there are other things we can discuss, is when will all the surface be saturated? When will all those sites be gone? So there aren't any more sites for sticking, and so the particles will come through, never find a sticky site, and leave. That's what we're trying to model. And so what we did in the lab was we ran, again, our same particles through, and we looked at, okay, everything is being caught, nothing's really coming through, or maybe just a little bit. But at this point, we see consistently that we get what we call breakthrough. We get particles coming out. So that's good, but that doesn't mean anything to any of you, or really to me, for scale up, right? Until we put a model to it. So we said, well, let's make it really simple. Let's just say there's a certain number of sites on the surface, and when they get filled up, it doesn't work anymore. And we're going to model that based on some F value, which is the maximum fractional coverage. So we can use the data that we got, and we can say at what point can we predict at this point where all these things break through, how much of the sand surface is covered with our particles? And that seems to be a consistent number, and we found it's about 4%. So when 4% of the surface is covered, then the things will break through. Okay, well all that allows us to do then is say, okay, if I make it bigger, we have even more surface area, right? And so we can predict how long it will take for those sites to be filled up. That's kind of what that model does. And we showed it's consistent, at least for these experiments. So you get some standard deviation here. Okay, so that then allows me to remember at the beginning I showed you this big claim that everybody thinks is crazy, but I'll tell you why I'm making that claim based on what assumptions. So now let's say, okay, you want to clean water for 1,000 people. We're going to, I'll tell you about the water in a second. We're going to use a typical sand, about 0.7 millimeters. These two things are from our model. This is pretty dirty water right here. This is probably even worse than primary effluent in our wastewater treatment plant, but just to show that we can do that. And then we're going to use a diameter of a particle of 1 micron because, like I said, that's the hardest to remove. And I guess I didn't put it in here. We're going to say 1,000 people. We're going to say 2 liters a day for drinking only. We can certainly change that. You know, these are just the assumptions that we did for the experiment here. And so again, we can put whatever you want in there and run it. And so it turns out that we need to make the column kind of big right now, especially for this size sand. So 1 meter by 1 meter, again, this is for 1,000 people, right? 1 meter by 1 meter is pretty big, I think, and we'll work on, okay, so, oh, here, I did do this. Okay, so if for 1,000 people, if we say 2,000 liters a day, then we choose the diameter of the column. Let's say it's 1 meter. We get whatever. Okay, and then we figure out how many seeds we need. And when we do that, we find out that if we have fully mature seeds, we just need the seeds from 6 trees. That's a lot of seeds. That's a lot of seeds. However, then we ran the thing to say, well, how long will it last? And this is where people say, you're crazy. Well, I don't know. It's a big column, right? So the surface area will last basically forever. So this thing will never get saturated. Well, what that tells us as engineers is when we design this thing, saturation is never going to limit us. The limiting part of this is we've got to get those pathogens to hit the sand. If it hits the sand, it will stick. But the problem is that whenever you have a sand column, there are voids. And the pathogens can freely go through there without even ever contacting a sand surface. If that happens, no matter how sticky it is, it's not going to stick, right? So that's why we have to make it big to increase the chances of it hitting a sand. So we've got some engineering work to do to see if we can reduce that. Of course, if we made the sand size smaller, so we go closer to a slow sand filter, that will work better. That's just, based on the model, because the void spaces are smaller. But as many of you know, if you've tried slow sand filters, that also means it is a slow flow, right? And so we have to kind of balance the practical piece of, do people really want to wait all day for 2 liters of water? How slow does this thing, or are they just going to get frustrated and just not use it anymore? So all of those practical pieces we're still considering. And we have been working on this for a while, and we've had students try to run these things in the lab, but without the pure science, we struggled. And that's why we've kind of gone all the way back to saying, okay, we've got to model this thing, we've got to get the science. Now we can start to push out a little bit beyond that to understand what's happening. So we've got some other things that we really need to be able to do. One thing we really need to be able to do is check viruses. We have some initial results that show that nanoparticles are being removed, which means that viruses can be removed. So we're really excited about this because no other sand filter can remove viruses. I know slow sand filters maybe can, or there's some discussion about that, but we think we can do it. The model doesn't predict it well enough. The model basically stinks for nanoparticles. That's a scientific problem that we're trying to fix, but we really think that we can remove viruses. I don't have the data on that yet, so that's a hypothesis only. But we're excited to start that work. Obviously, a little more complicated. I guess I didn't also mention in this, and I should have, we also put E. coli through there. So we put in 10 to the 8th E. coli, and none came out. We were like, we did 10 to the 6th first, none came out. We did 10 to the 8th, none came out. So we're like, we don't know what's happening there, but they're getting stuck. So the next thing is viruses. We need to get some training and figure out how to do that, but we're excited to do that. This is totally science-y, but one of the things that we're curious about is what is the mechanism of killing the bacteria at the surface? Because one of the cool things about looking at the antimicrobial mechanism is, at least the antimicrobial mechanism that we found, which is the fusion of the membranes, bacteria can't become resistant to that. So bacteria, if it gets in with the DNA and RNA and that kind of thing, then bacteria can find ways to get around that. But when you just puncture a hole in a balloon, it's hard to recover from that, right? And so that's kind of exciting. Again, hypothesis is to say that maybe this won't create antimicrobial resistance, although these little bugs have done amazing things to find ways to resist all the different things we've thrown at them, but we're hopeful about that. Of course, all of you hopefully are thinking, wait, you can't just go throw this at somebody. There are all kinds of other issues. There's social impacts, environmental impacts, and we certainly need to find partners to help us with that. And I have some partners even at Penn State starting to think about this from a bigger picture at that level. and really comparing this to other water treatment processes, many of which you have all looked at and discovered. And so, I'm not trying to say this is the best compared to all of those, but how do we compare this among all the many ideas that are out there for cleaning water? So again, I've worked with dozens of students. This was the first grad student that helped us. She's now working at a fragrance company. Actually, this student was the first undergrad to work on this, and she's actually out of grad school, been working in the field for a couple of years, so this has been going on for quite some time. It's just been a lot of fun to do this. And then I have to thank many of my collaborators. This is actually my husband, Daryl. Since I have about less than 5 minutes, I'll tell you a funny story about how I started this project. So I did all this literature review, and I had this idea about the sticky killer sand, but at the time, I was actually just teaching part-time at Penn State. I didn't have a research lab. I wasn't really, I was just teaching, and I just was fascinated by this. It was like my volunteer job to just go research stuff, right? Just, like you all, right? Just doing it for the love of it because I cared about it. And so I got this idea, and I went into his lab, and he was going to have a research meeting. He's a faculty member at Penn State, full professor distinguished. He's awesome, and taking care of all my kids while I'm here, so even double awesome. And I went to his lab before he got there, and all these students were there, and I started telling them about this great idea that I had, for making the sticky killer sand. And they were like, oh, that's so cool. And so he walked in just as I was saying, does anybody want to switch? Is anyone bored of their projects and want to come work with me on this? And he said, no, you can't steal my students like that. So I did steal his students. And these two were the first two that I stole. And no, this was his grad student who graciously worked on this on the side and still had her regular thesis. And then again, this is the undergrad that worked and took those first great pictures. And over time, I've gotten my own students, and so we've just really had a great time with many, many students working on this. Many of them have gone on to grad school looking at sustainable water treatment, and it's been really exciting. Okay, anyway, Manish Kumar is one of my colleagues also. He's doing a lot of the antimicrobial work. He grew up in a small village in India, and so he just has a passion for that as well. And then Mike Erdman is the head of the Engineering Leadership Development minor at Penn State. He's had many student groups work on this with us as well, and went to Rwanda with me. This is actually a picture of us going to Pivot. They take wastewater and turn it into fuel to burn for cement. It's a fascinating project. And then we also have worked with a psyllium oil in Rwanda. So they're growing lots of moringa trees and selling the oil to the body shop. I don't know if that's a secret, but I just told you. So the body shop has a moringa line, and starting in February, they're going to get all their oil from Rwanda, which is very exciting. And so I think that is all that I wanted to say there. This is sort of just another picture of the process.
Go. All right. Well, Dr. Yeah.